All right. Welcome back to the Ethereum Protocol Fellowship Study Group. This is week 6 and the start of the distributed tracks here. So today we will be starting the development track with Hsiao-Wei and Sam, creators and masters of the specs from the consensus layer and the execution layer. I think we'll probably get started with Hsiao-Wei first. Mario, maybe you want to give Hsiao-Wei a quick introduction.
Yeah, for sure. Again, welcome everyone in the week 6 of in the second phase of our program. We will have another talk on research domain on Wednesday, but today is Monday and we have the development track. And a very important topic that I believe that the Ethereum developers need to be familiar with. And these are specifications, so the consensus and the execution layer specification. And we are lucky enough to have basically creators of the specifications in Python here today, Hsiao-Wei and Sam. And one important note to start with: these are like two distinct projects. Like they kind of evolved separately, and the consensus layer is specs are older one, or the Python version is the what came first. Because Hsiao-Wei have been working on the research team. Correct me if I'm wrong, since like 2017, I think. Um, Basically creating the design of the beacon chain itself way before it launched, before the merge and everything. So she's been with us for many years now, and yeah, it's an honor to have you here. We'll learn about the technical side of the specs, and I believe that Xiaowei. Uh, we we have this call a bit earlier than normally because she's in the East Asia, and I believe that she's also hoping to have some maybe new colleagues or some new Ethereum developers from Asia. So I hope that our protocol fellowship fellows here get inspired. Yeah, yeah. Xiaowei, it's the stage is yours. Please go ahead.
Thank you, Mario, for the introduction. Let me share my screen just now. Mhm. Okay. Can you see it? Okay, perfect. All right. So my name is Hsiao-Wei. I work at the Ethereum Foundation Consensus R&D team. So it will be a lightning talk of the executable consensus PySpec. So it is totally open source as the most Ethereum core projects. We have like more than 100 contributors now. I think most of them are core devs that really need and use this space. And the license is totally CC0 open source Python project. So you can, if you see it on the GitHub category, then it is a Python project. Yes, okay. So you can use this link to see what it is, what it looks like. So for the Python spec, the CO spec, it has 3 purposes here. So first, the most important thing is the center of the Ethereum core consensus specifications, which means it defines the protocol in the files. And then the second is the most interesting part is it is executable and verifiable. It can be built into a Python program and then can be executed. We will talk about it in details later. And third, it's also interesting is it is also the test vector generator for the CO clients to test their implementations. Yep. All right. So whenever we want to add a new features like a new patch to the current mainnet protocol, we will open like create a new feature markdown file in the space, and we will write it in markdown file. For example, the last hard fork, it was the DNAP hard fork. So we are going to include like, for example, like EIP 6110, and then there will be a file, a folder called EIP 6110, and some files in it. Right. So, and the second, we will release the new PySpec with test vectors suite that. So the test vectors would be generated with the PySpec program test cases for client teams to verify. So this spec is like and nowadays is an important and unique component of the current CL R&D process. It helps us to found the basic bugs before client teams implement, because at the stage of writing the spec, we can test it. The client teams program will be, they can also use it to double verify it. So it's pretty helpful tool for the ecosystem. So I think people would wonder that why we use Python. So I think it is because the Python is the most readable language, one of the most readable language for the most developers, because like most pseudocode looks like Python. So we also try to write the spec code in the simplest way, instead of using some fancy, efficient Python magic. And yeah, so we do care about the readability and simplification first. So if you want to read it to understand one of the features and how you can browse it. So if you have the repository URL on your laptop, you can take a look that under the specs folder, there are the many hard forks. For example, like the Phase Zero, Altair, Beatrix, Capella, and DNAP. These are the hard forks already happened and launched on the mainnet. And inside there's inside the features folder, you can see some work in progress research project in it. And so, for example, if you want to read the Phase Zero specs, you can see there are like different markdown files in it. And the beacon chain .markdown.nd is the entry of the beacon chain consensus. So I would recommend, if you want to read it, and start from this file. And there are also other different components for the CL. For example, like fork choice, we define the fork choice logic in this file. And about the networking, it is in the P2P interface markdown file. Yeah. And also for the future different forks, it could be more different components that we will add in the future. Okay, so if you started to read it, you can start with the type and value definitions. We can see that we will define the constants and some configurations values in the markdown tables like this. So like what are the name of this basic custom type, and what is its SSD equivalent, and also like some description. And beside that, you can see we have the preset and configuration. That basically like the configuration that we set, but we will manage them in different ways. So the values are defined in these markdown tables. And then you can also see we have defined the XAZ containers in this markdown file. For example, there's a beacon block body and the beacon block, and the beacon block would use beacon block body in, you can see in the last field, it is body. Yeah, so the classes are the XAZ containers. It is also the serialization schema for the consensus objects. Yep. So if you want to understand more about XAZ, you can also find the documents in the same repository. Yeah, here. And okay, so we could write Python function in code block to describe the consensus rule. Can see this is an example of the entry of the state transition functions. There are some assertions, for example, like assert, verify, block signature, like so it is this condition that need to be satisfied in the consensus rules. So if this condition is not satisfied, it will throw exception. That means the given input is considered as invalid input. So you can use these assertions to see that what is the consensus verifications are. There are also some other valuable resources for you to learn the design and the deeper rationales. I would recommend like two resources. One is Vitalik's annotated spec, and another one is Ben Edgerton's Upgrading Ethereum book. Okay, so as I described them, the specs people see is, they are markdown files, but there's some magic inside this repository. I call them the spec elf. Like it basically we do something under the needs to pass the markdown file and convert the markdown file content into a Python program. So this is the build spec function, and so it will do something that the reader should know indeed. So for example, the phase 0 beacon chain ideally will be passed to the file itself will be passed to the spec builder, and then it became the phase 0 beacon chain spec. And then for the next hard fork, it's called Altair. It is actually like a extent of the previous hard forks. So the Altair hard fork will use the previous hard fork phase 0's content, and then add some extra modification into it. So like we combine both files and convert it into one single Altair beacon chain spec. And and the Bellatrix and the other following specs are doing the same thing, similar. Yeah, so last we want to introduce how to use PySpec. As a executable program. So you can install it from the source code and run this make file commands easily to install the required testing packages and build the PySpec. So you can try to write your first PySpec program. This is a Hello World example. You can import the basic spec of the basic fork. For in this example, it is the Bellatrix fork, and then you can import the components, the containers of this spec. For example, this is the beacon block body, and there's a field called graffiti. So you might add some graffiti like random string into it. Yeah, and the block itself it is an XSZ object, and you can print it out to your screen and see, yeah, I did put the string hello world into the block. Yeah, and if you want to try something more interesting, you can also write your first PySpec test. So this is what the one test case looks like. So it's basically a PyTest test. And if you have written PyTest, then you know it is simple. And what we do here is to prepare the block. So this time we build an empty block for the next start. The two input of these test cases, one is the spec, another is the genesis state. And we can, after you write some test, you can also verify if the post state is correct as you estimated. So you can write the assertion here in the last. And so in previous I talked about how to it is the also it I mean the PySpec is also the test generator. So actually we can reuse the PyTest cases to generate the test vectors. And the magical part is here is that we yield certain data out to so if I write yield pre-state here, it will output a file called pre.xyz, and it will be an encoded XYZ data, and it will be an encoded beacon state data in it. So in this case, we will yield one pre-state and the post state, and then the series of blocks that we will put into the state transition functions. So the client can get 3 of them, then they can verify if their state transition function is correct. Yep. Oh, right. And like this. This is the test vectors repository. So this is the example here. This are the output. Yeah, and if you are interested, you can find some more details of how to run PySpec and what are the test formats look like. Oh, and if you are interested in helping the CL research and development, I think PySpec is a pretty good, simple start to learn, and then you can go move to contribute. So I think there are like different levels of that you can participate in. So first you can look around and then maybe start with just a typo fix, or like for the layout, anything you can do. And the second is that you can probably help to refactor the code base. And then the level 3 is that you can try to hack some new edge test cases that we haven't covered yet. I mean, that would be really helpful to the CO clients. And the fourth is that you can probably submit a bug bounty if you found the bugs in the CO stack. Right. And thank you. This is my introduction of PySpec. Thank you. And Mario?
Yeah.
Thank you.
Awesome. Thank you so much, Hsiao-Wei.
Okay.
Yeah, it was awesome. Really appreciate it. Great intro. A lot of information. People are still kind of processing it. Maybe there will be some questions. But yeah, it's really great. I Yeah, I wanted to maybe ask if you can tell us maybe a bit about how the consensus specs interact with the execution side. For example, there was a question about the state transition function that you mentioned. I suppose that so the consensus layer updates the execution with the fork choice, but can you maybe elaborate a bit more about the interaction there, how the state transition happens on CL and it's mapped to the EL?
Yeah, okay, let me, okay, may have to share another screen. 1 second. Okay, so this is the CL spec index. So let's see the spec itself. So so here is the state transition of the beacon chain. So beacon chain will we have the pre-state and the side beacon block here, and then we don't have output here, but the state itself it will be modified during the state transition. So after we process slot and block and the result state, the same object will be updated. And about the relationship between it and the fork choice, you can take a look at the fork choice markdown file. So yeah, fork choice file is very interesting. So it file defines like what are the correct behavior that client should do when they receive a new block or a new attestation. Yeah, and so for example, if on the time that upon the time they receiving a block, they will call this implementation. So the client have different implementation to make more efficient execution. But PySpec is like we just want to define the rule clearly. And I think we have called the state transition, yes, inside the block function. So upon they receive the side block, they will do some verification for the fork choice. And if it's okay, then it will call the state transition here. Yeah, and then update the local database of the kind later. Yeah, I think. Yeah, did I answer your question, Mario?
Yes, I believe that was really great. Yeah, thank you so much. I appreciate you going through the actual repo and showing us the deeds. This is really great. Yeah. Yeah, we have maybe like 5 more minutes. Let's see if there are any more questions. Um, yeah. What about testing reorganization issues? I suppose you mean the chain reorgs. Um, yeah. Whether there is some sort of testing for chain reorgs, whether how the consensus specs handle reorgs.
Right. So in the Casper FFG implementation, so actually the folk choice is the Casper FFG LND and okay. Okay, 1 second. Okay, we can go back a bit to see the store. Yeah, so we define an abstract data class here. These are the fields that we want to describe what are the fields that could be used for handle the reorg and the state transition. So you can see we have stored like the justified checkpoint of the local view, the current view of the client, and the finalized checkpoint. And there are some, I think it would be more maybe too detailed, is that the unrealized justified checkpoint and unrealized finalized checkpoint. So, and also the blocks and the state. So the blocks are, it is actually a dictionary. So we use the block root as the identifier. And so does the state shared. The root is the block root of, and then the content is the state of the given block root. So you can see we have this kind of the fields. And then when we handle, where we handle the reorg, okay, so one second. Okay. Yeah. Yeah. So this helper will update the checkpoints. So it includes the justified checkpoint and the finalized checkpoint. And so you can see, you can search this function inside this document, and you can see where we update the checkpoints. So basically, currently the basic stable state we will use. We will use the justified checkpoint state as the basic stable state, but there's also the head of the state. So it will go through the series of LND ghost folk choice inside this implementation. And then in some certain cases, reorg might happen. So this is one of the edge cases here. Yeah, so basically you can find the code in, you can see how we describe the whole LND ghost in this folk choice document. Yeah, and if you have some more detailed question, and you can ask me in Discord or something where else. Thank you. Mario?
Yeah. Thank you, Hsiao-Wei. Yeah, that's awesome. It's amazing to see how you orient and explain the different parts. It's really great. I appreciate it. And maybe one last question we have from Sam here. What was the biggest challenge you faced when developing the CL specs? What did you find most challenging?
So, good question. The most challenging, I think, so performance, I think it would be the shared challenge for all the Python projects. And the second thing, for myself, maybe not for others, is like, as I said, that we have to convert the Markdown file into the Python program. But so for the spec writer, you have two choices. One is that you can update on the Markdown file directly, and then every time you want to verify it, you have to build it into the Python program. And then the second one is that you can probably write it on the Python program, but eventually you will have to write it back to the Markdown file. So I do feel it is a bit of tiring if you have to do this conversion, but that's my word for now. And yes, I hope I answered that question too.
Yeah, of course. Yeah, thank you so much, Hsiao-Wei. I think it was great. We are at half an hour, and really appreciate it. We have the Discord. I will share you the link, so maybe if there are some extra questions you can answer there. But this been really great. I hope there might be some contributors to CL Spec or somebody who learned the PySpec from you. Yeah, I really appreciate it. Thank you so much, and especially thank you so much for staying up so late for us tonight, or maybe too early. I'm not quite sure right now, but yeah, thank you so much. I appreciate it so much. It was really great.
Thank you, Mario. Yeah, and thank you, Josh. And okay, let's see Sam. Looking forward to Sam's presentation. Thank you.
Yeah.
Bye.
Thanks, Mario.
Thanks so much,
Are you
Hsiao-Wei.
with us? Thank you so much again. Yeah, and Sam, if you are with us, please join us on the stage. Can you hear us?
Yeah, I can.
Awesome. Yeah, so now we will move to the execution side of things with Sam here. And we are doing the execution second because they are also kind of younger, these specs, because Sam has been working on these for like maybe past 2 years or more. Correct me if I'm wrong.
Yeah, about that.
Yeah, Sam with his team, with all the other folks within EF have been developing the EELs, the executive execution layer specs, which are similar to the PySpec you just saw. And Sam, actually, you might know him from different places around Ethereum. He's also a very active EIP editor, helping to maintain the whole EIP repo with also with software, and also running the all wallets, helping to standardize and develop the Ethereum wallets around the ecosystem. So it's really great to have you here, Sam. And yeah, we are eager to hear about the execution specs, execution side of things. So
All right, let's see if my screen sharing works here. I want to share this one. All right, and let's make this there. Can everybody see that?
yeah, awesome. Go ahead.
Perfect. All right, so I'm here to talk about the Ethereum execution layer specification, or EELs for short. I'd like to start off my presentations with a very quick summary. So if you're only going to watch 30 seconds of this presentation, these are the 30 seconds you really want to see. So we started off with the yellow paper. It's written like an academic paper. It uses very dense mathematic notation, a lot of non-English characters in there. And kind of where we're going and where we are right now is a fully executable Python implementation of the Ethereum execution layer. These kind of pictures here just highlight, exactly what we can do. So on the left here, you can see kind of a diff between the preceding fork and the subsequent fork, and you can see all the differences there. And kind of a similar thing on the right. So this is what the specs looks like. This is what we've built. It's a regular Python program. And that's it for the summary. A little bit about me. I'm Sam Wilson. I'm an EIP editor. I work on a bunch of projects. You can find me on GitHub or on Mastodon. So what is an Ethereum execution layer specification? Well, it's a Python reference implementation of most of an Ethereum client. We do leave out some pretty important parts. We don't do networking. We don't do fork choice. We don't do reorgs. But other than that, we pretty much built the entire execution layer. The other members of my team are Guru and Peter. So if you ever have any questions about the spec, you want to contribute, you can reach out to myself or either of these two fine people, and we'd be happy to help you. And just like the consensus layer specs, we've had contributors from everywhere, from all over the world. There's even a POAP if people like collecting those. So yeah, so big thank you to all these people. And yeah, a little bit of history now. So the yellow paper was created in 2014. It's a little bit more restrictive license. It's attribution share alike, which means if you use it, you have to release your stuff under the same license, which is pretty decent for a specification, but a little bit annoying for code. Here I'm going to give you a really, really fast tour of the yellow paper. And the important thing here is I don't like the yellow paper, so I'm going to be a little bit biased in my tour. So to any appreciators of the yellow paper out there, I want to apologize. But let's get into that. So the yellow paper is mostly English text. It gives a lot of background, a lot of good rationale for why things are the way they are. It's also intermixed with very technical academic kind of notation here. So this snippet here is describing what a blockchain is. So Formula 1 here is saying that the state at time plus 1 is equivalent to the state at time with the state applying the state transition function to the state at time and a set of transactions. And then that might sound familiar to any of people familiar with blockchains. That's how they write it in the yellow paper. We also have a definition here of what proof of work is. And you can kind of see how all of that works. We also go into what the fork choice rule is, and you kind of describe how clients choose which fork to follow. And here we have a definition of the state. So this is probably one of my favorite examples of the yellow paper doing both an incredibly good job and an incredibly bad job at describing what the state is. So these English descriptions, they're amazing. They actually tell you what is in the state. You got the nonce, balance, or true code hash, all things that you're going to be familiar with if you're working with the EVM. But on the right-hand side, we have these incredibly dense notations that explain how the trie is encoded, which is number 8 here. And you'll have how the contract's internal state, its key value pair mapping, is encoded here. I don't know what those mean. I've implemented the Python version and I still don't understand what these functions mean. So that's kind of why the inspiration for trying to replace the yellow paper. Again, here's an example of what a transaction looks like. So we have our English definitions here, and they're fairly understandable. And then you have this lovely blob over here. So a transaction is a tuple of TN, TP, TG, TT, TV, P, TW, TR, and TS. And if anybody can remember what any of those variables mean, you guys deserve a prize. I don't. Again, the block, great description of all of the things that are in it. Super useful if you're implementing a client. And then you have the rest of the yellow paper. Gas, the entire virtual machine, how RLP works, precompiles, EVM instructions. It's all defined in the yellow paper. It's a very dense document. Yeah. Now, all of these formulas here are examples from the previous slides, and I've already forgotten what they mean. So that's kind of the biggest problem, I think, with yellow paper is that these notations, while they are very succinct, are very difficult to understand. So why, like, who's the yellow paper targeting? It's not targeting developers, and I think that's the biggest problem with it. Programmers are the people who need to understand it the most, the people who are actually writing clients. And then the other people who are using the yellow paper are EIP authors. So if you're trying to propose a change to Ethereum, you need to describe that change in some way. And none of these documents use the notation from the yellow paper. Half of any core EIP is defining a language to describe the change. Oftentimes that's Python. So we wanted to give a more formal notation for that. The yellow paper is English, so it's not testable. There's no way to write a test to make sure that a client conforms to the specification, and there's no way to use the yellow paper to fill tests. But to be fair, and I don't want to just rag on the yellow paper the whole time. It's very succinct, so it's only a couple pages, and it does a very good job of formally describing Ethereum, if you understand that kind of notation. And I think the most important benefit, as far as I'm concerned, is that the yellow paper is algorithm independent. It doesn't specify how things work, only the observable behaviors of it. And I think that's a really underappreciated benefit of the yellow paper, and something that we don't have with EELS. On that note, EELS was created in around 2021 by Consensus's Quilt team. Maintainership has been moved to the EELS team at the Ethereum Foundation. We're under a more permissive license. We're basically public domain. So, kind of why did we start making EELS? We wanted to escape the frustration of trying to understand the yellow paper. I've read it a dozen times. I have a hard time understanding it still. And I'm not an expert developer, so I kind of think I'm a reasonable representation of most people working on Ethereum. There's also no snapshot of the current state of Ethereum. So if you've ever read the yellow paper, you'll notice that it lags behind by a fork or two. Right now, it's only been updated until Paris, if I remember correctly. So you have to take the Paris yellow paper, find all of the EIPs that have come out since then, and that is how you figure out what the current state of Ethereum is, which is a little difficult. And we wanted something that is more up to date and provides kind of a snapshot of what Ethereum is right now. We want it to be more accessible to programmers. That's kind of like the number one goal, I guess. Python is very readable. The consensus layer specs were already written in Python. So we wanted to do that for us too. And then our final big, motivation for doing this is to be able to fill the automated tests. So Geth has been the reference client for a very, very long time. And we wanted to kind of have a simpler client that isn't cluttered with complexities of a real client, and that's kind of what we wanted to do here. So now it's now it's time to kind of give you a tour of EELS. So I'm going to give you rough example or rough equivalent to the one I gave for the yellow paper. The first thing I want to show is our directory structure. So we have a folder. We have a bunch of utility stuff like integer types and implementation of ethash. But most importantly, we have a folder for each fork. And each of these folders contains a complete copy of the Ethereum specification. If you were to take, say, just Paris and delete everything else, you would have a working implementation of the Paris hard fork. And that's kind of one of the big differences between our client and, let's say, Geth or Nethermind, is that Paris stands alone. You can read the Paris folder and get a complete idea of what Paris is. So this is kind of like what the blockchain implementation looks like in EELS compared to the yellow paper. We have regular classes that define what each data structure we need is. And then we have regular Python functions that define what the behavior is. So you can see, like, very similar to Hsiao-Wei's presentation about the consensus layer specs, we have our assertions that show what we check to make sure that the state transition was performed successfully. We have Python functions that implement little chunks of the algorithms that we need. And then right here in 194, that's actually building the blockchain. So we try very hard to keep it very simple Python, very easy to understand. So similarly here is validating the proof of work for a particular block. It's not exactly fork choice, but it's what we have. We don't we expect to receive only the correct blocks because we don't handle reorgs. That would be a whole extra complication in our database that we don't touch. But we do have a full state implementation. So all of the things you expect an Ethereum state to be able to do, we can do. And these are representations of our transactions. We try to have like meaningful names for all of our classes and all of their values. And here's a block just for completeness sake. It looks like a regular Python class. So the downsides to EELs. Obviously, it requires Python knowledge. It's written Python. If you want to contribute, you have to use Python. Whereas the yellow paper does, it is English, so you can just write text and have people understand you. We do require specific algorithm choices. So when the yellow paper can say, like, we expect X and Y to happen, we have to actually write a particular implementation of what X and Y is. And that can leak into downstream implementations, and that's something we have to be very careful about. It's also more verbose. We have easily an order of magnitude more code than there is text in the yellow paper, and it's less accessible to people who are familiar with the yellow paper. On the other hand, the benefits of EELs are that it's super easy to identify these things. These signatures and class definitions are very understandable to anybody who can read Python. You know that the first one here is the state transition function. There's no tuple of T subscript B or whatever. It's all very understandable. Understandable to programmers, which is important. And we already match what people do in EIPs. You can use actual Python. We're also more well-maintained. Where the three of us work full-time. Well, two of us work full-time, and I work most of my time on this. And it's very easy for anybody to contribute. We have people coming in and making drive-by pull requests pretty much all the time, and we're implemented all the way up to Cancun. So this is something I'm really excited about, and if I'm talking too fast, I have to apologize. But we can sync the chain. So you can take EELs, you can put it on a very, very powerful computer, and it will eventually sync mainnet. And that's something I think we're pretty proud of. It also passes the Ethereum tests suite. So every test that normal execution clients pass, we also pass those as well. And we can do the opposite. So you can prototype your EIP in EELs and use EELs to generate tests for other clients. Some other cool things that I think would be interesting to talk about that we've been working on. So diffs, this is my baby. I've been working on this for a while. Because each hard fork is a complete implementation of the Ethereum protocol, it's very hard to tell the difference between, to see what's changed. So this one here is an example of the DAO fork. We've written custom documentation tooling to generate these diffs, and you can see them on our website, which will be linked at the end. What else? We also participate in fuzzing. So this is a very recent feature. I think as of last week, we got this in. So all of the current execution clients participate in fuzzing, where random inputs are assembled and thrown at the client to see what happens. We participate in that now. So I think that's pretty neat. And it's already found a few bugs in our implementation and a few bugs in other clients. So yeah, that's about it for the formal presentation here. So I will stop at this point, take some questions, and then if there's still time at the end, I can do a demo of adding some stuff to EELs if people are interested.
Awesome. Thank you so much, Sam. Yeah, that was great. I appreciate it. Thank you very much. Folks, if you have any questions, feel free to ask right now. It's the best time. Yeah, meanwhile, I want to say that I'm very surprised that you sync the chain. I didn't know about that. It's super cool. How long does it take?
So we don't run it regularly. So I think the last time we synced it was 2 or 3 months ago, and it took 2 weeks or so. It's very slow.
Genesis?
Yeah. And like once you get up to recent blocks, it's like a block comes out every 12 seconds, and we complete a block every 10 seconds. So it's very hard to catch up, but we can sync the chain.
That's amazing. I mean, I didn't expected that Python client would be able to sync like the the modern Ethereum. I remember Trinity trying to do it years ago. I think they never managed to sync. So
Yeah, so there are some caveats here. We have like a 128 gig RAM computer with like very powerful processors. It's not an easy task. I wouldn't recommend anybody doing it, but it's possible.
awesome. Yeah. One question here. You mentioned that the EELs are up to date with Cancun, but in the repo we just see Shanghai. So where can we find the specs posted?
Yeah, so there is a fork/Cancun, or a branch fork/Cancun. We just haven't merged it into master yet. There's a few refactoring things we want to take care of, but it's all there.
Okay, cool. So it's the branch. Very well. Yeah, and also you mentioned that so there are things which are omitted from which are missing from the exec yields, like the peer-to-peer or the fork choice. Can you maybe mention where you can find specification for these? I guess there are the execution APIs specs as well.
Yeah, so the APIs are, like you said, in the execution APIs. There's the networking specification. I don't have a link handy for it, but it's under the Ethereum repository as well. And for the fork choice, we're just going to be adding English text describing how that works. It adds a lot of complexity being able to do rollbacks and switching between forks, and that's not something that we can really reasonably handle. Yeah.
Okay, awesome. Thanks so much. Any other questions, folks? Anything you'd like to ask?
Oh, actually, there's something I forgot to mention. So the consensus layer specs took the approach of starting in Markdown and rendering to Python, and we took the exact opposite approach. So we start in Python and render into HTML. So it's a kind of a very opposite approach. We have a Python first thing, and they have a Markdown first, and we both end up with, I think, reasonable documents at the end. It's just an interesting fact.
Okay, awesome. Yeah, it's an interesting comparison. Okay. Yeah, I would repeat the question that you asked Hsiao-Wei. What was the most challenging that you find? I mean, you mentioned issues with reading yellow paper and so on. Yeah, what do you find the biggest challenge of it?
So kind of a similar problem. Writing Ethereum, like the actual Python for it, isn't the hardest part of this project. It's all of the associated tooling. Being able to render everything. We had to build a whole new rendering system, a whole new documentation tool. That's been the hardest part. It's just making it presentable to people and accessible.
Yeah. It's been also a while, like before you started, and actually the specs was there, but then it got officially announced as like the released version, which is presentable. I mean, it took a while. It was a big amount of work. So yeah. Okay. Let's. Yeah, I think we can wrap up. There are just a few questions we can answer later. And we are at almost the hour, so yeah. If you have anything else you would like to elaborate on, show us.
Sure.
Also share the screen and show us some of the repo or some more hands-on coding example or anything like that. Like, we would be very thankful.
Yeah, I can definitely do that. So, just find the right window here. There we go. There we go. So, this is kind of an unrehearsed live demo of adding an opcode to eels. So we're going to start off by just, let me just move this over here a little bit there. All right, so you can get eels. Oops. There. So we're starting from scratch. We're cloning the eels repository, and we're going to go right into that. There. So now we have the execution specs repository, and we have to set up our virtual environment, which is the second step. So virtual environments, if you're not familiar with Python, are like a local package repository, so you don't mess up your system Python. So let's turn that on. There we go. So now we're in our virtual environment, and you can see that our Python is also sandboxed inside the virtual environment. So let's add an opcode. My favorite opcode to add is usually something like increment. Just pop a number off the stack and push one greater than that number back onto the stack. So let's do that. First step here is installing the project so that we can edit it. So we use pip as our package management system. Should be pretty familiar to any Python developers, but if you're not a Python developer, all you need to know is pip install -e dot. There we go. So that's installed all of our dependencies, gotten everything set up. We actually depend on the execution specs as well for their implementation of, I think it's KZG commitments. So yeah, we already share a bunch of code. So let's go and check out the Cancun branch, because that one's a fun one to start from. Yeah, instructions. So this is going to be an arithmetic instruction. So everything to do with the EVM lives under the VM folder. Hopefully that's an obvious choice. So this is what, resize this a second. Perfect. There. So here's the add opcode. This is the implementation. Every opcode is divided into the same 4 sections. We have stack manipulation, charging gas, the actual implementation of the opcode, and then incrementing or not incrementing the program counter. So let's copy the add instruction here and change it to inc. So let's delete the doc string here. There we go. So we're only going to pop one item off the stack, which is going to be the input number. We're going to charge the same amount of gas, which will be gas very low. And we will add 1 to the value we popped off the stack, and we will push it back onto the stack here. This only takes 1 byte to encode, so we'll leave the program counter at +1. Now, we have to actually tell the interpreter about our new opcode. So let's go and do that. That is in the init folder. So let's give it 0C as the numeric representation of it. So we have to add it to this enumeration of instructions here. And then we can go down and add the implementation. Yeah, which would be right here. So instead of ops sign extend, we have ops inc. And then we will have the inc instruction. And that is the entirety of adding a new opcode to eels. It is really a very simple Python program. There's no kind of weirdness to it. There's no performance considerations. Our version of the Cancun fork now has the increment instruction, and that's it. yeah, so that's pretty much the demo. If you ever have any questions or want to work on this stuff, please reach out to me. I'm pretty available on Discord, Twitter, whatever you like. Thanks so much for letting me demo that.
Awesome. Thanks so much, Sam, for
doing the demo. Yeah, I appreciated that you are able to just come in, do the live session, and show us code in EELS. It's super cool. And folks can try it themselves. Follow from the recording, I guess. Yeah, awesome. There was one question from Pooja here. I wanted to ask as an EAP and EELS person, because before the EAP ERC split, there was a talk about proposing EAPs with EELS. Do we see that in the near future?
That's question's kind of up in the air. So you can link to EELS from EIPs. So if you want to use code you've written in EELS in your document, you can. But the original vision of moving core EIPs into this repository is kind of dead. So think of EELS more as like one of the many ways to express your change, and not the only way to express your change.
Yeah, that's really cool. Yeah. Okay, I think we can wrap up. It's been over an hour, and we've learned a lot today. So yeah, thank you so much again, Sam, Hsiao-Wei, if you're still here and listening. Thank you to both of you. Huge thanks for demonstrating and explaining the both sides of the specs. So yeah, and thank you so much for all your hard work on the specs themselves. Like we have properly specified Ethereum finally, and it's there. So it's really amazing to even have that. So yeah, thank you all so much. Awesome.
Great. Yeah. Thanks, Sam and Hsiao-Wei, and we will see you all in a couple of days for the first session with the research track. I believe it is on starting with Denkrad.
It's dunk sharding with Denkrad himself on Wednesday, 4 p.m. So we'll continue the week 6 with the research track there. And yeah, guys, you've been the first to give a talk in our development track, so really appreciate it for empowering the future Ethereum developers, and also like the current ones. I believe like many people can learn from the talk there. So I really appreciate it. Yeah. Yeah, thank you so much, and we'll see you Wednesday and next week.
Thanks, everyone.